Thank you very much, Emmanuel. As he said, my name is Francisco Rodríguez. I work with Dr. Bob Storm at the Center for Digital Music of Queen Mary. And we work on the evaluation of applied machine learning algorithms, specifically for music information retrieval, something that before Professor Karen Wiggins mentioned. And I will explain a little bit for those that don't belong to the field what we mean by music information retrieval. So this talk is, well, this workshop is extremely interesting for me because I get a lot of input for my research. So thank you very, very much for coming here today. So in this talk, I'm going to present the case study that we conducted during the first year of my PhD, which I think it perfectly exemplifies the kind of, I would say, surprising and, I dare to say, undesirable shortcuts that machine learning models might take from our data for specific problems. But first, as I said, let me give you a little bit of context. Okay. What do we mean by music information retrieval problems? Well, in our field, researchers are interested in giving the resolution is not extremely good. Well, given thanks, sorry. Sorry. I don't know. In the video, there will not appear the introduction. Okay, it was not extremely interesting, I guess. Okay. So, as I was saying, in our field, researchers are interested to, given a wide variety of users, let's say listeners, composers, DJs, and whatnot, to try to provide them the music and information about music that better satisfy their particular needs. And in order to do so, we could try to annotate, to describe every single music item out there among all the vast amount that we have available nowadays. But that is not always feasible. For the scales we are talking about, we usually need to rely on developing automatic systems to help us do these annotations, these descriptions of the music items. And those systems, in the particular case in which those systems are expecting as input the audio signal, the audio representation of a somehow intangible music instance, as Professor Wiggins mentioned, the music is not something tangible, then we talk about what we call a music listening machine. And a music listening machine, what it does essentially is first extract some characteristics out of the audio signal, some features, which then are exploited by a classifier, usually a machine learning model, but it could be also an expert system based on some human-defined rules. But we will stick to the machine learning approach, supervised machine learning approach, to try to assign that item to a particular category. Usually we interpret those categories as some descriptions of this music item. Let's say that it's a rock song, that it's a happy tune, or that it's good for cleaning the house, or other more musicologically meaningful, like the tempo, the chords, or whatever. So, in order to know that these annotations, that these descriptions are useful for us, we need to judge them somehow. And usually the usual approach for evaluating those systems is seeing them as a black box, like feeding them with a lot of examples, and asking the system to provide some descriptions, some annotations, some predictions. In this case, in terms of the genre, rock, disco, country, and whatever. So then, an obvious way of judging that would be to ask someone, is that correct? Is that not correct? But as we have seen today, that's not usually the case. Usually, we replace the judgment of the user with some annotation of the input. In a certain data set, we have a collection of annotated recordings. We then, again, usually compute some performance metrics, as Sasha has just mentioned, precision, recall, F measure, and whatnot, expecting them to be, again, everything related, to reflect the performance of that system in some real cases. Bye-bye. Scenario. Sorry. But, as we have seen all over today, that's not always the case. Our data, our recordings in our case, might have some information on there that might be used by our systems to compute the descriptions, the predictions, or whatever we want to call them. This information might not be directly related with the problem we deal with, but in our specific data set might be correlated with the notations. In this case, we have a horse. This possibility that the systems behave like horses actually raises doubts about the generalizability of those results. But in any case, that's how people in our field do things most of the time. And usually when a data set is made public, sometimes this becomes the benchmarking data set, the one in which everyone needs to evaluate their systems. And the most widely used in our field is this one, JITSAN, data set that was released in 2002, and for the problem of music genre recognition, same thing we were talking about. And it has 1,030-second clips of 10 classes. We have here, I don't know, rock, pop, jazz, whatever. And it has been used in at least 100 different publications. We have here the highest accuracy that those publications reported, from around 40% to almost 100% out there. This is not ordered by chronologically, it's ordered simply by increasing accuracy. But seeing this chart here, we would expect, oh, we have almost solved that problem, as Matteo before mentioned it in the sense of sound environment. But what happened here? It happened that none of those publications took into consideration what was actually in the collection. The collection contained some distortions, some duplications of the recordings. And in fact, this collection doesn't control for the repetition of artists. It means that one person trying to classify in terms of genre, or thinking that it classifies in terms of genre, could be using the cues, for example, the timbre of the voice of the singer, or some other artist-related things, in order to do the predictions. Whenever we have, or it has been reevaluated, those systems, taking into consideration those faults, those problems of the data set, in every single case, the performance has dropped quite substantially. That could make us think that these systems are actually somehow horses. They are relying on information that is not important for the task, not important for music genre, in order to drive those super beautiful results. And around 2 years ago, in 2014, I don't know if it's seen properly, but Joachim Anden and Stéphane Malat proposed a new system, a system based on scattering features and support vector machines that reach more than 90% of accuracy in this problem. This is pretty nice, not the highest, but those ones are a little bit problematic in general. Which, according to this precision, this accuracy, they claim that they were useful for that. Those features were useful to recognize the music genre. But knowing that this data set has problems, we wondered, well, will these systems also show the same problems we have seen before? Well, not. And because all the code was available online, so we could completely reproduce all their experiments. But also we wanted to take advantage of that and go a step beyond. Not only wanted to know how much will they fall, if they will fall, but also we wanted to know why the systems were reaching those accuracies. Something that has been mentioned today all the time. Not only how much, but why. So in order to do so, we took the following approach. We started by opening the black box. We started for looking inside the system, trying to dissect it in what we said before, the extractor, the classifier, see how each of those parts might potentially contribute to the results we observe. And with that knowledge and the knowledge of these problems of the data set, drive some targeted intervention experiments. What we refer to as intervention experiments, well, we mean altering some part of the system, let's say of the classifier, or its environment, for instance, the audio recordings, the content of the audio recordings. And if we don't see any difference in the performance results, then we can be pretty confident that that thing we altered wasn't contributing to that. If instead we see a difference, we can guess, we can be pretty confident that this thing we changed was actually contributing to the results. We see here 6 different, what we call feature sets. There are 6 different configurations of the systems. The first one is what they use as a baseline. The other 5 are actually scattering feature systems. So first we started by taking a look at the audio features, the characteristics that they extract from the audio. And that's kind of the schematic representation of the maths behind that. I will not go into detail. That's not the purpose of the talk. But what we see here is that given us some input, the time representation of the signal, each layer in this cascade performs wavelet transform and the complex modulus. That's not extremely important right now. What I want you to remember is that those 2 layers here correspond to what we call a B vector, 85 dimensions. If we add a further layer, then we have a C vector. If we added more, we will have an F vector. And if we use the frequency representation, we will have D and E vectors. But we wanted to go beyond that. We didn't trust completely that. We went inside the code and we checked how those things, how those wavelet transforms were actually computed. And what we saw was that they were simply filter banks, simply. Each of those dimensions here corresponded to the output of one of those filters. And interestingly, all those ones here, that's the first layer, out of 85, 12 have center frequencies below 20 Hertz. Why is that important? Those are frequencies that, in theory, humans cannot hear. So that doesn't mean there is actually any information to be extracted from there. That doesn't mean that if there is information, that it will be useful at all. But that was something that kind of clicked in our brains. If we see it a little bit more closely, these dimensions, all those ones here in red, correspond to both in first layer B vector and C vectors, correspond to frequencies, to filters around frequencies we cannot hear at all. So there is the potential of some information that it's supposed to be relevant for the task that could be captured. So knowing that the data set has some problems, knowing that there is this potential for capturing information irrelevant, we drive our intervention experiments. And the first of them attempts to target to this one here. Do the problems of the data set affect these particular results? To do so, we do what we call the partitioning intervention. We compare 2 ways of splitting the data set. The first of them, what we call random, is simply assigning at random of the 1,750 to train, 250 to testing. That resembles what is usually done and how it was done in the original publication. what we call fault or fault filter selection. That is, we changed the dataset so that it didn't contain any distortions, it didn't contain any duplications, and we made sure that there were no errors replicated from among train and test sets. Obviously, that affected the contents of the dataset. It reduced its size and changed a little bit the balance. But what we saw here, first thing, results, that in every single case, there's a decrease in accuracy, as we saw in the examples before, in those arrows before. In every single case, there's a drop. In some cases, higher, in some cases, lower. So we can be pretty confident that the faults also affect in this case. The next intervention that we performed was to replace the classifier algorithm. Why? Because support vector machines, even though they are pretty popular, they have usually achieve high results, they are not easily interpretable. And we wanted to know which features were more important, and we wanted something cheap to train and test so that we could try different subsets of features. And that's what we saw. First, when we used the whole vectors, we see that there's not a large difference. There is a difference. There is a decrease between the same condition. It's a little bit higher between fault and fault. But it seems that, well, support vector machines are contributing, but the features are actually driving the predictions. But the interesting thing, as I said, happened when we trained and test using subsets of features. Those are the 85 dimensions of the first layer, B vector. If you remember the numbers that I said before, first dimension, the DC component, by itself, one single feature, something that comes from the DC component, by itself, almost 30% of accuracy, by itself. Next one, the one around 2 Hertz. I don't know why they ordered it that way. It's dimension 85, by itself, even higher, even closer to 30%. So it seems that there is actually information below 20 Hertz in those recordings that the systems might exploit. Interestingly, in both cases, we see the biggest drops between random condition and fault condition. This seems to imply that there is certain correlation between this information below 20 Hertz, that it's there, no one knows why, and the partition condition and the faults of the dataset. In fact, if you group together all those dimensions that correspond to frequencies below 20 Hertz, only those ones with a binary decision tree, one of the simplest learning algorithms you can imagine, more than 60% by themselves, which is roughly the same accuracy that was reported for this dataset in the original paper, which for people in our field is somewhat shocking. So we see that even though the changing the classifier algorithm didn't affect much the results, but we got some information that we can drive forward. We know that there is actually something there that can be potentially used by the systems. But we still don't know if the systems, the original ones, actually exploit that or not. So last of the interventions we did, well, let's check if that information actually affects or not. So what we did was to attenuate the information was there in the recordings. In the test recordings, we applied a Butterworth filter, not worry about the details, so that all the information below 20 Hertz was at least reduced 30 dBs. We checked that there was no acoustic difference, so that we haven't introduced any artifacts in there. And we used the systems trained with whole information and tested them all using the filter versions. And we saw that between random and random, especially in the first layer, from around 80% of accuracy to 31%. In those ones, the decrease is lower, but still it's evident. But we see that if we then control for the faults of the data set, that goes down even further. First layer to 22%. Even though those two possible confounding factors, the faults of the data set, the information below 20 Hertz, seem to be correlated, we see that they are not exactly the same factor. So, we see that both the faults of the data set and this information below 20 Hertz, that no one knows where it comes from, are actually influencing the results we observe. At least in my opinion, that means that the systems are actually horses. Are using information that is not related with the task, with the music genre, in order to achieve those results. But this way of approaching the evaluation, not only relying on the numbers and that's it, it's not only useful for detecting horses. It's also useful to provide improvements. For instance, what would happen if we train the systems without that information? Well, it's something that is worth trying, something that we wouldn't have guessed. I suspect that no one in our field would have suspected that the systems were using that if we only relied on the numbers. So, what I claim is that by using system analysis and generation experiments, not only trusting the numbers, we can get relevant information from our evaluation. And it also highlights some validity issues in the original evaluation that was performed and that is usually performed in any system in our field. But at least in my opinion, the main problem of this methodology is that it might not be extremely systematic. It relies, in our case, in a lot of luck in finding that there were filters there that no one had cared about. So finding a way of doing that in a more systematic way, it's probably something that I will need to address in my research. And so something that a lot of people has asked me when I presented this work is that, well, now we know that there's the information there that no one had before considered. What else can be there? Which other confounders, which other sources of horses could be there hidden in our data without us realizing? Is there any way of finding all possible? At least if not with a community effort, I don't think that's even possible. And the other question I need to address in my research is how come proper experimental design, in the sense of statistical experimental design, can help us to avoid these problems happening again. And that's all for my part. That was a pretty short talk. Thank you very much. I'm open to any questions and suggestions, criticisms. And just in case anyone wondered, an actual horse, a real animal, the frequency range starts at 50 Hertz, so not even a real horse could have listened to those frequencies. Thank you very much.